Good afternoon, everyone, and welcome to NASA's Johnson Space Center in Houston, Texas. I'm Sandra Jones, and we're here today to talk about the the return-powered flyby that occurred earlier today. We're going to start with a few folks that are going to give some opening remarks, and then we'll open it up for a question and answer session. This return-powered flyby did commit Orion to returning back to Earth. But first, I'm going to introduce our briefers. First up, we have Mike Serafin, who is the Artemis mission manager from NASA headquarters. We also have Judd Freeling joining us, who is a flight director here at NASA's Johnson Space Center. We have Debbie Korth as well. She's the Orion Program Deputy Manager here at NASA Johnson. And joining us virtually is Melissa Jones, the Landing and Recovery Director at NASA's Kennedy Space Center in Florida. If you are a media personnel that is wanting to submit a question, you can do so by pressing *1 to submit your name into the queue. If you do find your question has already been answered, you can press *2 to remove it. And for our media here in the room, we'll also be coming to you. So I'm going to turn it over to Mike to give some opening remarks. Mike?
Okay, well, good afternoon, and thank you for continuing to follow the Artemis program and the Artemis I mission. We are on flight day 20 of our planned 26-day mission, and we continue to proceed along the planned mission profile. As Sandra indicated earlier, we did successfully complete the return-powered flyby and are now committed to an Earth return trajectory on the 11th. As we've talked in the past, we've had a number of commitments to each and every one of you, and one of those involved what we call sharing remarkable images. And if we could queue up a series of images here, we've got a brief collection. And this was taken on flight day 6, is the Orion spacecraft approached the moon, and the Earth is way off in the distance. You can see 8 million people off in the distance, and a human-capable spacecraft about to circle the moon in the foreground. And this is one of those remarkable moments and remarkable images that we got to share on November the 21st. A little farther along in the mission, on flight day 13, we got to witness as Orion flew about the distant retrograde orbit, which is the farthest point that a human-capable spacecraft has ever flown. We got to see the Earth transit behind the moon, extending beyond the pale of human spaceflight, what a human-capable spacecraft has done. And then earlier today, we got to see a flyby of the moon as part of the return-powered flyby, and witness the Earthrise for the first time in the Artemis generation. And here you see the Orion spacecraft near the point of closest approach, and then this is the Earthrise that we witnessed. Orion's in the foreground, the Earth is in the distant background, and the moon is in the middle there, and you see the crescent Earth. These are just a few of the remarkable images that we've been able to share throughout the course of the mission. When we are done with this mission, we will have traveled over 1.4 million miles in the course of the 26-day mission, and we are on track to do that. In terms of activity within the mission management team, since the last time I was here to talk to you on November the 30th, we did not meet on Thursday, December the 1st, largely because the mission has been going well. We did meet on Friday, December the 2nd. We had a non-decisional meeting for about 40 minutes, and we just statused the progress of our flight test objectives throughout the course of the mission, and then some of the anomaly and funny activities that we've been collecting along the way. We did not meet as a mission management team over the weekend on Saturday, December the 3rd or the 4th, largely, again, because the mission has been proceeding well. We did have a little excitement over the weekend that I'll talk to you about here in a few minutes. But today we did have a decisional meeting. It ran just shy of 3 hours, and the decision was to commit to deploy the recovery forces out of Naval Base San Diego, and our recovery director, Melissa, is here to talk to you about some of the preparatory activities and what's ahead there. But we agreed to deploy the recovery forces on December the 7th. And we also closed an action item as it pertained to some testing of what's called the pressure control assembly on the service module that the team had asked to perform as part of the testing on the return leg. We also reviewed some anomalies from over the weekend. We did have a unplanned communications outage at the Deep Space Network Goldstone site in California. There was a site-wide outage at Goldstone due to some hardware that's used to process the site and antenna angles. That was recovered last night, but on Saturday we did have a 4.5-hour comm outage. And as part of that, I do want to thank our friends and family in the Science Mission Directorate, as well as our flight ops team and the Deep Space Network team for working together to minimize the impact. Originally, when we learned about the Goldstone outage, we thought it might have been up to an 8-hour outage, and it might have been more than one day. But because of our friends in the Mars programs, Perseverance, and then the Trace Gas Orbiter, loaning us some of their Deep Space Network time, but then also through the ops team and the Deep Space Network team working to mitigate the site outage, we only saw a 4.5-hour outage on Saturday. Shortly after the site outage, we were proceeding. The flight team was proceeding through a test of the power system to further investigate a funny that we had seen earlier in the mission, a reoccurrence a number of times on what's called a latching current limiter, and we were in a test configuration. And when we were in that test configuration, shortly after we came acquisition of signal on Canberra, after the Goldstone outage, we noticed that 4 of the feeder current limiters had tripped off, and it had dropped some of the downstream equipment there. So we talked through that today as a mission management team. The spacecraft is fine. There's plenty of redundancy on the vehicle, and that in combination with timely work by our operations teams resulted in no mission impact and no concern there. We did learn a few features about the system as part of that. So we talked through those anomalies that occurred over the weekend. The Orion team in particular put in considerable time over the weekend, as well as our friends at the Deep Space Network to work through those anomalies. As a mission management team, we will continue to meet this week. We still have one active anomaly resolution team. We might hear the outbrief tomorrow regarding the active anomaly resolution team, and it has to do with the power conditioning and distribution unit and these latching current limiters and some of the anomalies and funnies that we've seen throughout the course of the mission. And then we have one remaining decision gate coming up that's a pre-planned decision gate, which is to select the landing site. And our entry flight director, Judd, as well as our recovery director, Melissa Jones, will come to the mission management team on Thursday, December the 8th, and bring forward a recommendation on where to position our recovery forces and to set up a meet-me date with the spacecraft from an entry trajectory standpoint, and Judd will elaborate on that further. We still have a few primary objectives ahead. The mission is going very well. We've accomplished a number of bonus objectives above and beyond what we had planned pre-flight, but we still also have some risks ahead of us. We still have yet to accomplish the second half of our Priority 1 objective, which is to demonstrate the spacecraft at lunar reentry conditions, as well as our Priority 3 objective, which is to retrieve the spacecraft post-splashdown. So with that, I'll pass it back to you, Sandra.
Thank you, Mike. Next up, we'll hear from Flight Director Judd Freeling, who was the flight director on console during today's return-powered flyby burn.
Thanks, Sandra. Let's see if we can throw up the video that Mike showed previously about the pre-RPF video. I'll talk a little bit about that as we were coming into RPF today. So this is a great shot coming in before we did our RPF maneuver. You can see kind of there in the lower middle there. We think that's the Copernicus crater there. That's pretty near the Apollo 12 and 14 sites, and we're just stunning video that we captured as we were about to go into LOS for our RPF burn. So RPF was the largest burn that we've done to date. It was a little over 962 foot per second burn, lasted 3 minutes and 27 seconds. That was on the backside of the moon. We had a loss of signal during that time period. But then as we came back, AOS at that time, and Mike showed that video as well, we saw a really outstanding shot of the crescent Earth, and it was just stunning. The RPF maneuver that we did behind the moon is essentially our deorbit burn. So this sets us up for the landing trajectory that's going to occur on December the 11th. Where we have a fixed trajectory, and so this is what that trajectory is going to look like. It's a little hard to make out, but the line in the middle of the page is a blue line that we will target our entry interface, which is at the bottom of this chart, which is about 3,500 or so nautical miles south, almost due south of San Diego. That EI time we're targeting for 11:20 Central Time on the 11th. And we will perform a skip entry, and that'll show you the next slide what that looks like from the side view. We just prior to entry interface, we will separate the crew module from the service module. That's about 20 minutes prior to EI, and then once we hit entry interface or EI, we'll be about 40,000 feet above the Earth's surface, and that's the top of this, the top left of this chart. We'll be traveling a little over 24,500 miles per hour. We'll also lose signal due to the blackout of the plasma ionization from the intense plasma that we're going through. This heat that's going to develop on the from entering the atmosphere. That first blackout will last about 5.5 minutes. We'll continue down for 5.5 minutes. We'll dip down to about 200,000 feet, and then we'll roll the capsule to create a lift more in the up direction. That will take us to our skip apogee, and we'll gain signal back right before that skip apogee. Skip apogee is around almost 300,000 feet. It's at 292,000 feet above the Earth's surface. Once we get to that skip apogee, we'll roll the vehicle again and start modulating that lift vector back towards the Earth. And then we'll develop on that downslope another blackout due to plasma ionization. That will last about 3 minutes and 15 seconds or so. As we continue down, heading towards San Diego, we'll go through various milestone points along the way. By that 150,000 foot mark, we'll be traveling about 8,500 miles per hour. Once we hit about 100,000 feet, we'll be traveling close to 2,400 miles per hour. Then by 50,000 feet, we'll be a mere 528 miles per hour. And then for our four-bay covered jettison, which will uncover the parachutes, the drogue chutes and the parachutes, we'll be traveling about 285 miles per hour. And then once we get our main deploy of our chutes at about 5,300 feet or so, we'll be traveling about 128 miles per hour. So there's a lot of numbers there, but really you take from 400,000 feet, you're traveling 24,500 miles all the way to splashdown where you're traveling about 20 miles an hour. So it's a lot of energy that we're dissipating at that point. As Mike alluded to, we'll prior to that point, Melissa Jones and myself will find a meet-me place for the recovery forces, so we make sure that we're all going to the same site. We do have the options of either landing a little short, and that first slide that I showed you where we could land short up to 1,200 nautical miles uprange of San Diego, or we can land a little long in what we call the northern weather alternate site, and that's right kind of the cover of the Catalina Islands there, just to the southeast of those Catalina Islands. So we have a couple options. We have Plan A, Plan B, Plan C, depending on the weather, to make sure that we're not only within capsule landing criteria, but also that we have the recovery criteria that Melissa and her team are looking to recover the vessel. So looking forward to getting to the 11th, and with that, I'll hand it back to Sandra.
Thank you, Judd. Next up, we'll hear from Debbie Korth, the Deputy Manager of the Orion program.
All right, thank you, Sandra. Good afternoon. Thank you guys for joining us today. I'm really excited to continue talking about our Artemis mission. As is mentioned, we are 20 days into our 26-day mission, and looking over the objectives on the spacecraft, we couldn't be more pleased about how the spacecraft's performing, really beyond all our expectations. As far as flight test objectives, we're about 30% complete with another 30% underway, and the rest ahead of us. As we mentioned, a lot of those are tied to the reentry phase, the landing, and recovery. No major issues. As you've probably heard in some of these conferences, we've added another 20 or so objectives because things were going so well, and most of those objectives are tied to looking at how we can expand the envelope and support our future missions. So Artemis I is just the beginning of a series of increasingly complex missions, and so we're really using this spacecraft to really push the envelope and see what we can get in terms of performance for power and thermal and propulsion and all the other systems on the vehicle. So did want to talk a little about what we learned in DRO. You know, we spent a lot of time in DRO and went through several flight test objectives, added 7 in that phase. A couple of key things that we did learn in that phase. One is we did some additional test objectives on our aux engines, and so we were looking at longer burn times that we know we're going to need for future missions. So to execute Artemis I, the aux engines have only burned about 17 seconds at any one given burn, and we really need 100 seconds for some of these future missions. So spent a lot of time burning that longer, looking at how that performed, and also looking at solar array thermal effects with those longer aux burns. So really good initial look at the data there. Looks like we're about within 10 degrees of our predicts from pre-flight, and so no issues there in that thermal response. Another item that we looked at as far as looking forward to Artemis II was the surface module heater config test, and so we actually configured the heaters for both the prop line set points and the water line heaters to the Artemis II settings, and what we saw is significant 70 to 90 watts of power savings. So again, the vehicle, we're getting much better thermal response than we had originally anticipated in the model, so this will help us refine those models and be able to offer more capability as we move forward in the future missions. So today we've talked about the successful RPF burn. It's 3 minutes, 27 seconds. The delta V was 961 feet per second, just almost spot on to what we expected the OMZ performance to be. And there's also been 3 return trajectory correction burns that we've done as well, exercising the SM-RCS system. So if you want to pull up the goodbye to the moon video or picture, this is what we saw today as we were coming out of the loss of signal, getting acquisition of signal. So I think you've seen this video, and I think everybody in the room, we just kind of had to stop and pause and just really look at, wow, we're saying goodbye to the moon. It's been a phenomenal 20 days, but we got a lot of work ahead of us still. So see, I'll jump a little bit to one of the main, I guess probably the primary anomaly that we are looking into. Mike talked about this PCDU user load, the latching current limiters that opened, 4 of the 5 that opened. And so, first of all, no mission impacts. There's a lot of redundancy in the system, and the systems performed as they had been designed using that redundancy. But we did find that we had a couple impacts there. We first of all, the RCS string, when that power reset happened, the flight software, as it's designed to do, says, well, we have to switch strings because the RCS isn't responding the way we had expected. When that power drive electronics came back on, we switched back to the primary string, and what we found was that was in a standby mode, so it wasn't actually able to fire the jet. So long story short, we had 6 of the 12 RCS thrusters that weren't firing, but the team saw that in the vehicle response, and able to command back to the primary, the string B of the RCS and continue with the firing. So no issues there. Again, showing we've got the redundancy in the systems we need. What we learned from that is we've got some fitter improvements that we need, the flight detection, isolation, recovery improvements that we need to do going forward on that system. The other thing that we learned from that anomaly was we had some heaters that were both tied, both primary and tertiary heaters that were tied to the single PCDU, and realized that when that PCDU went through this kind of power, this kind of power anomaly, we wouldn't have had the redundancy that we thought in our heater system. So we've actually already rechannelized those to give us back the redundancy that we expected to have in the system. So once again, I think that's probably the primary anomaly that we've been looking looking at. The team is working in the labs today and tomorrow to do some ground testing, to look at maybe some proposed testing we might do on board to kind of prove out what we think the root cause of these power upsets were. So again, the vehicle was able to respond and we continued the mission, no issues, but we are looking at the next few days if there's something that we want to do while we still have the service module, do some testing and first do that in the laboratory and get that on board in the next couple of days. So looking ahead, we have a few key things that we'll be doing on this return part of the mission. So talk a little bit about some of those objectives that we have planned. First of all is one of those would be a solar array wing modal survey repeat. So we did a modal survey very early in the mission and have decided to add back a second one now the end of the mission to see how the structural modes have either changed or degraded potentially. Again, this will help further reduce our risk for Artemis II. This is a long mission with a lot of burns, and so those solar arrays have seen a lot of activity in terms of movement, and so this will give us a good indication of whether or not we see degradation over a 26-day mission. We've also planned some new prop system leak test, and so on the MON and the MMH PCA branches, we have a latch valve and a couple of solenoid valves on each branch, and looking at actually confirming the leak tightness of those. We know what the leak rates were prior to the mission, and so we can actually go exercise those and see if we've seen any degradation there. Again, playing forward to how those are going to perform on future missions. So if you go ahead and pull up the image of the crew cabin, we haven't talked a lot about what's going on inside. We get these beautiful images of the moon. So you've probably seen this image. This is from the crew cabin. You can see our Moonican Campos, the Callisto payload, and other activities going on. So as we're coming back in, we've talked a lot about our primary test objective on the reentry. So the one thing we are looking forward to tremendously is the heat shield test. And so this is the first flight of our block architecture heat shield, and we'll be getting the first test of that coming in at 5,000 degrees Fahrenheit, the 25,000 miles per hour that Judd mentioned. And so we'll be able to see the performance of that and play forward for Artemis II and beyond. Parachute deploys. It's 11 parachutes that get deployed in a very rapid dynamic sequence, slowing that vehicle down from the 300 miles per hour to less than 20 when it hits the water. So definitely be looking at all that parachute performance. And then finally, our uprighting system. So the crew module does have these inflatable bags that help keep it uprighted if it does flip over, and then keep it upright. So we'll see the performance of those as well. So all that'll be happening inside the cabin here. You see the mannequin. There's several things that we'll be getting data back on when we get the vehicle back. The seats are instrumented with loads or accelerometers, strain gauges, so we can get loads and vibrations data. So on that impact, when we hit the water, we'll actually be able to get the data on how those loads are actually translating through the seat into the crew member, and also our radiation payload. So we're flying some radiation protection vests on one mannequin. One mannequin doesn't have them, so we'll be able to actually see how was the radiation protection. We get radiation environment data off of an item called HERA, but we won't have the actual vest data till we get down. So all those things are happening inside the cabin, and we'll be able to get that data back upon recovery. So and again, this is the first of many missions. It's not over yet. As you can see, we got a lot of objectives ahead of us, but I'm looking forward to that beautiful splashdown on the 11th. And so back to you, Sandra.
Thanks, Debbie. Our final briefer today is Melissa Jones, who is the Landing and Recovery Director at NASA's Kennedy Space Center in Florida, and she's joining us virtually today.
Good afternoon. The Artemis I recovery team is currently in San Diego. We've been here since a little bit after Thanksgiving. Last week, we performed our final mission rehearsal with the USS Portland, who will be the recovery team for Artemis I, the recovery ship, excuse me. We spent 3 days at sea with them. I think you have some video footage that was sent ahead of time. If you want to play that, we can talk through some of that. But we had a great 3 days working with them to refine our procedures and integrate our team so that we can meet the objectives of recovering the Orion spacecraft. You could see how they have a well deck underneath their flight deck on their ship, which is really why we picked this ship to work with. And there's our mock-up capsule. And so what we do is we will watch the Orion splash down and go out and attach some lines to the capsule and flood the well deck and bring that capsule in and put it down in the cradle. That's kind of hard to see there. So there's a lot of line management, but we had a great 3 days working with them. We started slow with line movement and capsule movement in the well deck, and the last day we did a full mission profile, which involves communication with the Mission Control Center and Judd's team, launching helicopters who are going to take all of the imagery and gather a lot of the flight test objective data that Debbie was talking about. This mission is all about gathering data, and so the timeline for recovery will be approximately 6 hours as we capture a lot of that data for our flight test objectives. We'll be very careful with the capsule, get about an hour and a half of imagery of that heat shield she was referring to before it touches anything in the ship. We want to make sure we document every bit of that so that we have the data that Orion needs to understand the performance of the capsule going forward. And then we'll very slowly do recovery into the well deck and bring Orion home. And so we are ready and honored as an integrated team to bring Orion home on the last leg of her journey.
And thanks to all of our briefers for those initial remarks. As a reminder, we'll be taking questions on our phone bridge as well as here in the room. If you are on the phone, you can press *1 to submit your name into the queue. And if you do find your question has been asked, you can press *2 to remove it. Once your name is called, please state your name, your affiliation, and to whom you'd like your question to be directed to. But we're going to start here in the room with a question.
Excuse me. Thank you, Mark Karoth, Aviation Week and Space Technology. How would you sort of assess or perhaps give a grade to the propulsion system overall at this point in the mission? It seems like you've, climbed Mount Everest in a sense, and but there's still some to come and maneuvers, maybe not with the drama that you've done so far, but you want to get her back. So I'm just wondering if you can offer a.
You want to start?
Yeah, I'll say as the operator of the system, I'll give it an A. Certainly, everything the vehicle has asked for us to do, it's done, and it's done phenomenally, right? So we've done all of the burns up till this point flawlessly. We've added some extra tests on it, even for the Plus X auxiliary engines test that we did, that performed flawlessly as well. So yeah, it's really great performance. I'm happy with it. I don't know, Debbie, if you want to say anything else.
Second that vote, and thanks to our European partners for their provision of that European service module. So that whole propulsion system is designed and built by ESA and Airbus and delivered to us and installed in our vehicle. It's been great, and I think we've added some objectives. We actually have another one on part of the return leg that we didn't talk about. During the DRO, we did some tail to sun maneuvering of the OMZ to see, if we could get a larger operating box on that tail to sun, and we're actually going to do a pure tail to sun on the way home because it is just performing really well. So I think because we haven't had to be troubleshooting anomalies or things, we've been able to look at how can we expand that envelope. So it's been very good.
Yeah. And Mark, for context, we talked prior to the mission that this was a stress test with Artemis I. In order to get into and out of the distant retrograde orbit, we had to fly 2 large propulsive maneuvers to get in, 2 large propulsive maneuvers to get out, plus multiple correction maneuvers on the way out in the distant retrograde orbit and back. It has performed throughout. So in order to execute, as Debbie alluded to earlier, increasingly more complex missions throughout the manifest, we know we have to enter a lunar orbit, which requires a 2-maneuver sequence, and exit, which requires a 2-maneuver sequence. We successfully demonstrated that with the European service module throughout this flight.
And we do have another question here in the room.
Hi, Eric Bird with Ars Technica. A question, I think, for Debbie, but just on the power issues you were talking about, and I appreciate you sort of going into that. If there had been astronauts on board, would they have noticed anything? Now, it's like colloquially, like the lights flickering, or you mentioned something about the RCS, thrusters not coming on. But what would they have experienced, and would it have been handled automatically, or would that have been some kind of consultation with mission control? And is this, and just sort of in addition to that, is this something that's at all a concern as you look toward Artemis II, or do you think that this is some kind of software issue or something like that can be addressed relatively easily? Yeah,
I would say, first of all, we're not concerned. I mean, we think we know in the failure detection response what we need to update there to make sure that it's picking up this standby mode of the PDE, which caused it to continue to try and fire these thrusters that actually couldn't be fired. But it was easily corrected and switched over to the other string, so no concerns there. So in terms of what the crew would see, I probably would have to lean on my FOD friends, but yeah, go ahead, answer.
Answer that. So they certainly would be notified of the issue on their onboard displays, caution warning displays. We'd certainly have a message, but they would follow their procedure, and it would tell them reclose these latching indicators, and we're all good. In the meantime, they would have lost no capability.
Our next question will come from the phone bridge, and it's from Bill Harwood with CBS.
Yeah, hi, guys. I appreciate this, but if I could maybe let Mike take a crack at explaining the anomaly. I mean, I realize it didn't have any effect on the mission per se, but I really don't understand what the issue actually is. I mean, what's the power control and distribution unit not doing? What's being limited? I don't understand any of that stuff. If somebody could break it down into high school terms for me, I'd appreciate it. Thanks.
Yeah, Bill, thank you for the question, and I'll probably ask Debbie for a little bit of help here on this one. But the service module receives power that's generated through the solar arrays. The solar arrays, in turn, have these latching current limiters that provide power into the power conditioning and distribution units that are then distribute the power throughout the spacecraft. And when it's distributed, there are different avionics boxes or power loads, and what we saw were 4 of these feeder current limiters that tripped off in close sequence while we were in this test config. And the test config was we literally took one of the power conditioning and distribution units, and there's a side and a B side, and we isolated it to gather some more data. So normally there's what they call a split tie across that A and B side within the first power conditioning and distribution unit. We split the bus into 2 separate bus ties, and then on the 1B side we saw all 4 drop on the power conditioning and distribution unit. And when that happened, all of the lower level power systems, or all the lower level avionics, in one case, it was the propulsion drive electronics, a redundant unit that provides drive electronics to 6 of the 12 thrusters. That also went to standby because it had dropped off, as well as some heaters, as well as a number of other lower level loads. So we don't quite understand what caused the latching current limiters in this case to trip, let alone that many in close proximity. We're still gathering data on that. Debbie has an active anomaly resolution team within the Orion program, and I guess I'll pause there and see if you have anything to add on the description of the problem or any additional information.
I think that's a great description of the problem, and I kind of think of it as like you've got your power. If you look at your house, you've got a power supply company, and then you've got a breaker box in your house. And so in this case, it's almost like those breakers opened, and what it appeared is that they were commanded open, but there were no commands sent. So the question is, we're still in the middle of the investigation on why that happened. So you still had power coming from the arrays. You still had your PCDU. You have 2 PCDUs, so you had your redundant systems working, but because those switches opened, you now have equipment that's looking for power that's not getting it, right? And so typically then your fault recovery system would switch to a system that can give it the power, because we do have everything redundant. So not exactly sure on the root cause yet, and so the team's doing some testing in our offline labs today and tomorrow, and then likely proposing some tests that we can do on orbit later this week before, we discard the service module, so we have a pretty limited window if there's anything we want to do before that happens. So like I said, not sure on root cause yet, but that's kind of how, at a high level, that's how I hope that helped.
Yeah, and Bill, one more point here. In your house, a light switch or a circuit breaker, that is the command device. You literally flip the switch, and it closes the circuit, and that is the action or the command that does it. What is a little bit odd to us is there's no record of a controller on board the vehicle sending a command to open the latching current limiter. So in your house, the device is the command object. In this case, there's a separate controller that tells the current limiter to open or close. and there's no record of the command device saying you should open or you should close. This thing is just open or closing without this box, the command device, telling it to do so. So there's some anomalous behavior here that we're trying to understand.
Our next question comes from Gina Sensuri with ABC News.
Thank you very much. Can you just run through the numbers for me? Speed on reentry, temps, all of that stuff. Give me those numbers if you don't mind.
Yeah. Sure, Gina, no problem. So when we come into entry interface, we're at an altitude of 400,000 feet, and we're traveling approximately 24,529 miles per hour. Once we get to skip apogee, which is about 7 minutes 19 seconds after entry interface, we're at an altitude of 291,382 feet, and we're traveling at 16,824 miles per hour. At 150,000 feet, we're traveling approximately 8,547 miles per hour. At 100,000 feet, we're traveling 2,398 miles per hour. 50,000 feet, we're traveling 528 miles per hour. And when we jettison the forward bay cover at approximately 22,845 feet, we're traveling 285 miles per hour. And then our main shoot deploy is approximately 5,320 feet. And that's we're traveling 128 miles per hour. And then we hit splashdown approximately 20 miles per hour.
And just to add a point here, Judd, I think you said 16.8 is the skip apogee velocity. 16.8 is just shy of what a spacecraft comes back from low Earth orbit at. So that's our second dip into the Earth's atmosphere, is about what a low Earth orbit vehicle would come back at, which is 17,500 miles an hour.
Our next question is from Brett Tingley with Space.com.
Hi, this question, I guess, is for Melissa Jones. It was mentioned earlier in this conference that there's still a pre-planned decision gate ahead that will help select the landing site. I'm wondering, by what metrics or what criteria are the different landing sites selected?
So that's actually something that Jed Freeling and myself work on together, and it's mostly based on weather from my perspective, and there's, I'm sure, many other factors from the flight side. Jed, I don't know if you want to add anything to that.
Sure, Melissa. So we have a designated primary site that we try to land at first, and that's called San Diego Site 3. That's within the Fleet of Hot area, which is the fleet training area, hot as in hot munitions. So that is controlled by the Navy. So that's our first target that we try to land at, assuming that the weather and criteria is all favorable, not only for the hardware of the capsule, but also for Melissa's team to recover the capsule once it's in the water. And then we have various other sites within, as I mentioned, that northern weather and alternate that we could potentially go to within the San Diego area if the weather happens to be better than our San Diego Site 3. And then if none of those sites look good to us, then we can always go further uprange along that track, that kind of south to north track that I showed you in my previous chart, anywhere. Right, that's the one. So you've got a short distance there that's around 1,200 nautical miles that we would still be able to get our skip entry objective for the flight, and then. The only reason we'd go any further uprange of that is if we had something wrong with our navigation system. We had inertial measurement units. If we had more than two or more down, then we'd either do a ballistic or direct entry. So all that to say, we look at the best weather along that track, and we find the best weather. If that best weather happens to be San Diego Site 3, we'll go there, and otherwise we'll find a better place to land within those criteria.
And maybe expand on the weather just a little bit. It's wind speeds, but it's also wave height, wave period, because as we hit the water, how the capsule actually impacts that wave, where its height is, what you're on the back side of the wave, the front side of the wave, how the winds all respond. So it's a pretty complex set of parameters that we look at to say that you need to stay within this wave height, this wave period, this wind speed. So that's how all that plays into where we finally select where to come down.
We do have another question, this time from Alan Boyle with GeekWire.
Thank you. I guess this question would be for Debbie. It's about Callisto. Can you say anything more about the performance of Callisto? And is this something that you've decided could be used on Artemis II, or do you have to wait to see what the performance is and what the objectives are for that kind of communication system?
Yeah, so first of all, in performance, so far it's been really great. I've got to witness several of the sessions. Very, very interactive, very engaging in terms of being able to talk to the spacecraft, turn lights on and off, write notes, play music, ask questions. It's a really very good engagement opportunity, and I think it has some potential on how we would use that further as a digital assistant or some other onboard activity. There isn't any specific plans for Artemis II yet. We're waiting to get back the data from this flight to see, how it worked and what we can learn from how it performed. But so far, the performance has been really, really nice.
Our next question comes from Jim McDade with 1819 News.
Congratulations on breaking so many records on this mission. It's been spectacular. First of all, I'm Jim McDade, 1819 News and Verity Space News Clearinghouse. Apollo 13 set the reentry speed record back in 1970 after it got on its free return trajectory. And I'm given to understand that will be one of the last, if not the last, records that this Orion, that this Artemis I mission and Orion will break. Will future reentry velocities be comparable, or is it possible there will be even faster? Or is this another example of you pushing everything to the limits in this shakedown cruise?
Let's see. So I'll answer that one. My expectation is that the future missions for Artemis will be similar speeds to what we're entering here, if not less. It's all going to depend on the specific trajectory that we fly, and of course those are still being developed for individual missions, but my expectation is that they will likely be no larger than the speeds that we're entering for Artemis I.
Yeah, I think we definitely have some limitations or requirements on our heat shield, and so when we look at the reentry, part of the skip reentry is getting us slow enough down so that the heat gets down. So I think when we look to futures, I know we're trying to expand the skip distance for future missions, but I don't think that's going to affect the speed much on that.
Our next question comes from Sophie Sanchez with Cosmic Chicago.
Hi, thank you for taking my question. My question is for Debbie. You mentioned a couple of system configurations set for Artemis II that you've already tested. I was wondering if there were any that you were planning for the duration of the mission on the return home, any systems that you were planning on testing for at the Artemis II settings? Thank you.
I don't know specifically if we're testing Artemis II settings on the way home, but there's a lot of things that we are testing so we can expand the operating box that Artemis II can operate in. So things I mentioned like the solar array modal survey, understanding how the solar arrays degrade over time, these pressure control assembly within our prop system, leak checks, how do valves behave over time. This OMZ, we're orienting to tail to sun directly to see how we can get more performance out of the engine. There are some mixed string RCS firings we're going to be doing on the way home. So there's a lot of objectives, not specifically putting things in Artemis II configuration, but driving the system beyond maybe where we thought we were going to operate for Artemis I so we can expand that box.
And Debbie, I'll add to that. This is really the start of a campaign of several missions to get humans back to the moon and beyond to Mars. for Artemis II, there's still a lot of things still to test for Artemis II. We don't have a life support system on Artemis I, and so that's going to be the major objective for Artemis II is to test that life support system. We'll also be testing rendezvous and prox operations. In other words, rendezvousing with another vehicle when we rendezvous with the interim cryogenic propulsion stage on Artemis II. So there's still a lot to be done, and this is just the beginning.
Yeah, and Sophie, I'll just give you two more as part of a preview for entry, descent, and landing day that we're planning for here on Artemis I, and I think both these happen on Judd's watch operationally. One is an aerothermal test during the entry, descent, and landing, where we deliberately fire all of the reaction control system thrusters in various points during the reentry profile to gather hypersonic aerothermal data as we fire those thrusters. And then post-splashdown, we're deliberately going to keep the vehicle powered, assuming the vehicle is healthy, for 2 hours after splashdown to understand how much heat has soaked back after that peak heating of up to 5,000 degrees Fahrenheit outside the vehicle. As the heat shield protects the vehicle, there's still going to be heat that soaks into the structure that is the Orion capsule. It'll splash down in the ocean. The ocean's going to cool the vehicle, but some of that heat is going to be resident in the structure of the vehicle. So we want to understand how hot the cabin's going to get. So we'll leave the vehicle powered for 2 hours, keep it on the cooling system for 2 hours to understand for astronauts on the very next mission what the temperature profile in the cabin is going to look like. So that's part of that 6-hour recovery time frame that Melissa highlighted earlier. We're deliberately going to wait for 2 hours with the vehicle powered on the surface of the ocean. So those are some of the things that are ahead of us as well.
And that was the final question that we received this evening. So thanks to all who submitted questions, as well as our briefers for joining us in a busy time. Next up, we continue to look forward to Orion's return home. We'll have another briefing this Thursday at 4 p.m. Central, where we'll go over that return in a little bit more depth. And we'll also be covering Orion's entry, descent, and splashdown beginning at 10 a.m. Central on Sunday, December 11th. But until then, be sure to follow along with our daily blog posts as Orion continues its journey home at blogs.nasa.gov/Artemis. Thanks again for joining us. That will wrap up today's briefing.